Good afternoon, everyone. I hope you're having a wonderful Tuesday so far. I have another addition to our physics playlist here, and it covers a concept that we haven't seen yet involving banked curves, and specifically how static friction works on them. Now, this problem is a bit long and involved, so I'll just cut straight to the chase and get directly into it. Here we have a curve with a 120-meter radius on a level road that's banked at the correct angle for a speed of 20 meters per second. And if our car rounds this curve at a faster speed of 30 meters per second, well, what's the minimum coefficient of static friction needed between the tires and the road to prevent it from skidding? And we need to report the answer using two significant figures. Since banked curves are directly related to circular motion, it's probably a good idea to recap on some quick things worth remembering. Whenever an object engages in circular motion, you might recall that that object will experience a centripetal acceleration which points towards the center of the circle, like this. We also know that F equals ma, Newton's second law, that works in circular motion as well. And since the acceleration vector points towards the center, well, that equation means that the net force vector is going to point towards the center too. Lastly, the velocity vector of the object as it moves around the circular path, that vector is going to be tangential to the circle at every point, like this. So just a couple things to keep in mind as we move forward with banked curves. Speaking of banked curves, there's actually three cases involved that we should be aware of. We're going to use two of those cases in our problem, and since I'm showing you two, we may as well see how all three work as well. As you can see here, the first case involves no static friction at all. The car is going to take that curve at exactly the right speed of 20 meters per second, and it won't slip up or down. Let's get a free body diagram going while we're at it. First things first, create a set of coordinate axes. Notice that we will not be setting the x-axis at an angle this time, like you may have seen in some of those previous ramp problems. If you drew your axes off to the side like mine, just be sure to superimpose another set onto the car taking the curve. As you might expect, we have the car's weight pointing straight down and the normal force pointing perpendicular to the curve, like this. That is it for the vectors. There's no more occurring in this particular case. Unlike in the situations with ramps in the previous problems, we do not break the weight vector into components this time. That's why the problem description mentioned that the car is on a level road. Instead, we're going to break the normal force into components with the angle found here. This means that our cosine and sine components of that vector will be found in these spots. And a good question, and a common question, that I've been asked when tutoring these problems is, why are we putting the angle here? This seems a little weird after all the ramp problems where we typically had an angle located down here, right? Well, we can see that when we put the angle here, the cosine portion is going to balance out the car's weight, which will keep it in contact with the curve as it goes around. But the sine part plays a very special role here. It's what's responsible for imparting the car with the centripetal acceleration, which points towards the center of the curve, which is occurring in the x direction here, according to my drawing. And that's it for the first case. Let's check out the next one. In this one, the car is not moving at the perfect speed anymore. In fact, it's taking the curve so slow that the car wants to slide downwards. Thankfully, static friction can prevent this. All the vectors are pretty much the same. Okay, the weight still points down, the normal force is still perpendicular to the curve, and the components of the normal force are still there. And the static friction here, the breakdown of that is also pretty straightforward, so nothing too complicated occurring in this case. Let's check out the remaining one. Finally, we have the opposite situation where the car is trying to take the curve faster than the proper speed. Okay, so this is what we're going to use when it starts bumping its speed up to 30 meters per second. Notice that the static friction now points in the opposite direction because the car is moving so fast it will slide up the curve unless static friction can keep it restrained. With all those covered, let's come up with a strategy. Remember that we weren't given an angle for our curve, but that's okay though, since we can solve for that using a sum of forces analysis on case 1. Then, once we know the angle, we can move on to this case, case number 3, to figure out what the magnitude of the static friction is. So, like you have seen many times already, we start off at the top with our vector equation for F equals ma, and we split it off into chunks, starting with the sum of forces in the x direction. The only thing that points in the x direction is the sine component of that normal force, and that's equal to our ma portion here on the right hand side, where a is the centripetal acceleration. Let's replace the centripetal acceleration with its definition, v squared over r. Notice that I'm using the subscript of I here on the v, since this represents the safe speed of 20 meters per second. That's all we have in this direction for now, so let's investigate the other direction next. As I mentioned before, we have the cosine portion of the normal force balancing out the weight, which we can slide over to the right-hand side like this. We're at a bit of a standoff here since we don't know theta or what the normal force magnitude is, so it's time for another trick. Let's underline both of these equations and bring them onto a fresh slide like this. Here's what we're going to do. I'm going to divide the top equation by the bottom equation, and this way we can eliminate the normal force and get a useful trig identity out of it. Here's the first step. Next, I'm going to replace the weight with the definition, mg. You can see here that the mass is going to cancel out on the right-hand side too. So when we do that, we no longer have a normal force or a mass, and we've taken our trig identities and turned them into a tangent, because sine over cosine is equal to tangent. Next, I'll take a tangent inverse of both sides, and we can plug in all the information we've been given so far. We end up with an angle that's just shy of 19 degrees. And I'll hold on to a couple extra significant figures to make sure we get the correct answer in the end. Now we're ready to tackle the hard part, and that's case number 3. The force analysis of case 3 itself isn't too bad. Okay, we're still breaking up the sum of forces into x and y components like we did before, starting with the x, but this time we have to include the cosine component of the static friction, which is located here. Let's simplify this expression a bit and include the proper definitions for static friction and the centripetal acceleration. Notice that I've changed the velocity now to v sub f, which represents the car taking the banked curve at the faster speed of 30 meters per second. One last thing we can do is factor out the normal force on the left-hand side, since both terms there include it. And that's it for this direction. Let's move on to the sum of forces in the y direction. It's a pretty similar approach. Just be sure to include that sine portion of the static friction in this expression, which points down, so it's negative. I'll move the weight over to the other side first, and then replace things with the proper definitions. Notice we also have a normal force in both terms on the left-hand side again, so we can factor that out as well. Let's underline these two expressions and bring them onto center stage on a fresh slide. We're going to have to do the same kind of trick again. Okay, so just like in case number 1, the idea is to divide the top equation by the bottom one, which will look like this. When we do that, the normal force and the masses will disappear just like we're used to. Take a look at the right-hand side though. This part looks a little familiar, doesn't it? Here's a reminder from what we had before. The real difficulty behind this problem is figuring out a way to shoehorn this reminder definition into what I have circled in red on this right-hand side. If we don't do that, we can't properly solve the problem. Trust me, I've tried. So let's do the following. Pay close attention here. Here in the numerator, on the right-hand side, I've taken the final velocity, divided it by the initial, and then multiplied it by the initial. It might seem like a bit of math nonsense since we're not really changing anything here, but check this out. Since these two things here are multiplied together, I can factor out this final velocity divided by the initial velocity, which is squared since it's inside this squared parentheses. And now I'm left with what's exactly the same form as our reminder up here. Okay, so that's cool. And our reminder says that this part is equal to the tangent of theta. So let's make that change. I'm running out a bit of room here, so let's continue on a fresh slide. Here's what we just had. Notice we have all sorts of trig identities in this equation now. Okay, we've got sine, we've got cosine, and now we have tangent. Too many different trig identities can quickly lead to trouble. So let's change that tangent back into sine divided by cosine. Okay, we're allowed to do that. We might be able to get something more useful with that. In fact, what I'm going to do is multiply both sides by cosine, which will move it into the numerator up here, and divide both sides by sine, which will put it in the denominator over here. And that's what this looks like. Next, I will distribute these identities into the parentheses that they're attached to, which will look like this. Now, I'm going to multiply both sides by the portion in the denominator here on the left. And that will bring us a little closer to our goal, which is to get at mu sub s. To get that, though, I need all the mu sub s terms on the same side, which means I'll need to distribute this squared fraction into both terms in the parentheses, which looks like this. Now, we can exchange this cosine multiplied by sine term on the left-hand side with this mu sub s chunk on the right. And finally, all the mu sub s terms are hanging out together on the right side. Well, on the left side. Hopefully you know what I mean there. Let's continue on another fresh page. Here's what we had. And with this expression, we're now completely free to factor out mu sub s from both terms, which will look like this. We can also do a little housekeeping by factoring out the cosine multiplied by sine terms on the right-hand side, as you can see here in this next step. All that's left is to divide both sides by everything in these giant parentheses here on the left, like this, and plug in all of our known quantities. Be sure to do this very carefully on your calculator, and also check to make sure that your calculator is set to degrees and not radians. When I do this, I get the following value. And remember, we only need two significant figures, so if we truncate it accordingly, we get the correct answer, 0.34. And that's it. We're now done with our problem. Thanks for watching, everyone. Have a good day.